Innovation Spotlight. ReforMax and AmoMax. Innovative chemical technology in the fight against hunger. Today, 7 billion people are living on Earth. By 2050, this figure is likely to reach 9 billion. To feed all of these people, despite decreasing agricultural areas, crop yields will have to be increased by efficient fertilization. A humble molecule will play a central role in achieving this goal: ammonia. This substance is processed into various artificial fertilizers, such as ammonia fertilizer, urea, and other agricultural and industrial chemicals. The fertilizer industry consumes about 1.2% of annual global energy production, and 87% of this for ammonia production alone. In this process, the simple starting materials, natural gas, water, and air, pass through several stages to finally produce ammonia. In the primary reformer, the natural gas, methane, is transported with water vapor through pipes filled with Clariant catalysts of the ReforMax series and heated to about 800 degrees Celsius. Most of the starting materials are converted to carbon monoxide, carbon dioxide, and above all, hydrogen. In the downstream secondary reformer, air is added to initiate the oxyhydrogen reaction, in which temperatures of above 1,000 degrees Celsius are reached. The remaining methane gas is converted by ReforMax, and essential nitrogen is added. Ammonia can only be synthesized from nitrogen and hydrogen if carbon monoxide and carbon dioxide are first removed in different purification steps. What remains is atmospheric nitrogen and hydrogen that are forced together under high pressure and transferred to the ammonia synthesis reactor. Here, nitrogen and hydrogen react at an average 450 degrees Celsius to produce ammonia. The gas mixture thereby circulates through 2 or 3 catalyst beds. Compared to standard processes, the highly reactive AmoMax catalyst allows ammonia to be made at lower pressure and lower temperature, which means much less energy input per ton of ammonia produced. A catalyst is a substance which speeds up the rate of a reaction without being changed itself. The main constituents of AmoMax are the iron oxide-containing mineral wustite and 2 types of specially designed promoters that considerably increase the effectiveness of the catalyst. Structural promoters act like spacers in the voids between the iron particles and thereby greatly increase their surface area. In addition, electronic promoters enhance the reactivity of the active centers of the catalyst. When the hydrogen and nitrogen formed in the previous steps come into contact with these active centers of the catalyst's surface, they attach themselves to the surface under its strong influence. The bonds between the atoms inside the molecules, especially of the nitrogen atoms, are initially weakened and then slowly completely broken. The atoms are mobile on the surface and can approach each other. Hydrogen atoms form bonds with the nitrogen atoms, during which they lose contact with the catalyst surface. With the third hydrogen atom, ammonia molecules are formed, which then detach themselves from the surface and create space for new nitrogen and hydrogen molecules. The larger the catalyst surface, the more reactions can take place simultaneously. With the catalyst AmoMax, Clariant has succeeded in replacing the magnetite-based catalysts, which also contain iron oxide and have been in use for about 100 years. Wustite, in combination with optimized promoters, enlarges the total surface area of the catalyst and increases the number of active centers. This results in a 40% higher activity, a shorter activation time, and a correspondingly improved energy efficiency that is simultaneously eco-friendly and resource-conserving. Clariant is thereby helping to make food supply in the future a lot safer and more environmentally friendly. Clariant.